Thank you. So I can just try and... Okay. Thank you very much. Can you hear me? Thank you for the invitation. It's a great pleasure to be here. First time in Seoul. Okay, so today I will talk about cluster promotion maps. So in the last couple of years, there's been two main threads in intersection with amplitudes and algebraic combinatorics and geometry. One related more to positive geometries, the other related to cluster algebras. And for me today, positive geometry means amplituhedron. And basically, both objects have been very important, both in the math and physics community. And in the last couple of years, I've been interested in how the amplituhedron and cluster algebras are connected with each other. In particular, today, I will discuss mostly some work in preparation. It's going to appear soon, called Play-Big Tangles and Cluster Promotion Maps with my collaborators, Evan Zohar, Sherman Bennett, and Tesler and Williams. And also mention previous work that is also related, that appeared in the Proceeding on National Science, Proceeding on National American Science. Okay, so I will start with background on the positive Grassmannian, amplituhedron, and cluster algebras, and then I will move to explain how this is related to scattering amplitudes in n equals 4 superior mills. And finally, I will mention, I will talk about cluster promotion maps, and I will give an outlook. Okay, so I will start with the Grassmannian, fixing the notation. The Grassmannian GRK, n is a space of k-planes in n dimension, and we can represent an element of the Grassmannian as a full rank k times n matrix C up to row operations. And we want to consider specific special coordinates on the Grassmannian called Plucker coordinates, which are just the collections of all the k times k minors of the matrix. And I is the column set that we use to compute the minor. So if you have a matrix 2 times 4, the minor 1, 2, with columns 1 and 2 is 0 in this case, and these other minus 1, 3 is going to be the minor with column 1 and column 3 is going to be 1, and so on. So we want to consider all the collections of these minors as coordinates on the Grassmannian. In particular, we want to consider a subset of the Grassmannian where all these coordinates, Plucker coordinates, are non-negative. And this is called the positive Grassmannian. This is denoted in this way. And we can partition the positive Grassmannian into pieces according to which Plucker coordinate is 0 and which Plucker coordinate is strictly positive. And we can label, for example, the cell, this piece, according to the labels of the Plucker coordinates that are strictly positive. So, for example, here, this matrix here belongs to S sub m, where m is the collection of all labels except 1, 2, because 1, 2 is 0. And all the others are positive. So we can partition the Grassmannian, positive Grassmannian into these pieces. But the nice thing is that if we do that, Poznikov showed that whenever these pieces are non-empty, they are topologically very nice. But also we have a very nice decomposition into cells that are called positroid cells. So the positive Grassmannian can be decomposed in this way. And the nice thing is that these cells have a very nice combinatorics that are basically in bijection with many combinatorial objects. So for today, I will consider Play-Big graphs that are useful for labeling these positroid cells. A Play-Big graph G is a graph embedded in a disk such that each vertex is either black or white, so it's bicolored. And it has vertices on the boundary labeled from 1 to n, and they're incident to a single edge. So this is an example. And there is a bijection shown by Poznikov between the positroid cells in the positive Grassmannian and equivalence classes of Play-Big graphs that are related by certain moves. So here I illustrated some, this is not strictly necessary for our talk, but there are some moves that you can perform, and if two graphs are related by these moves, they're considered to be equivalent. In particular, we can label each positroid cells according to the equivalence class of Play-Big graphs. And in particular, so we'll denote S sub G as the positroid cell associated to a certain equivalence class of graphs. And a graph G, Play-Big graph G, is said to be of type Kn if the corresponding positroid cell is inside the positive Grassmannian k, n. So here it's going to be like 2, 8. Okay. Also, another thing is that we can always pick a representative in our equivalence class such that our Play-Big graph is bipartite if you consider black vertices at the boundaries. So in particular, here we can add some black vertices using this move that doesn't do anything, such that everything is bipartite, meaning each edge is adjacent to a black and a white vertex. It's going to be useful later. Okay, so let's move to defining the amplituhedron. So if we fix three positive integers such that k plus m is less or equal than n, and we fix a matrix Z that is n times k plus m that has all maximal minus positive, we can use this matrix to define a map from the positive Grassmannian that we saw before to a smaller Grassmannian k comma k plus m, just simply by matrix multiplication. So if we have an element of a positive Grassmannian, we multiply it, right multiply by the matrix Z that we fixed, and we get an element in a smaller Grassmannian k comma k plus m. And the image of this Z tilde map and of the positive Grassmannian is the amplituhedron. Okay. So if we specialize to known families, if some certain value of parameters, for example, k equals 1 and m equals 2, we get a convex polygon. For k equals 1, we get a polytope, it's called a cyclic polytope with n vertices in n dimensions. And for the maximum value of k, we get back the positive Grassmannian. For intermediate values of k, the amplituhedron can be seen as a generalization of a polytope inside the Grassmannian. There are also other values of parameters for which these are giving interesting objects. So for m equals 1, it's related to the cyclic hyperplane arrangement. M equals to 2, with some collaborators, we show that it has some connection with the hypersimplex and the tropical positive Grassmannian. But today we will focus mostly on m equals 4 because it was conjectured by Niemer, Kahneman, and Trnka in 2013 that its volume somehow gives the three-level scattering amplitudes in planar n equals 4 superior Mills, for where n is the number of particles and k that appears here is related to the helicity sector that is called the NK-MHV helicity sector. In particular, we can compute the volume of the amplituhedron by tiling it and summing over the volume of each tile. So we want to somehow learn how to decompose or subdivide the amplituhedron into pieces in order to compute its volume and hence the scattering amplitude. So we want to consider how to subdivide it, and there is a natural question, since the positive Grassmannian has a decomposition into cells, can we use their images under the Z tilde map to decompose the amplituhedron? This motivates the definition of tile. So if you have a positoid cell S, its image in the amplituhedron via the Z tilde map is called a tile if it's full dimensional and if the map Z tilde is injective on S. And a collection of tiles that is not overlapping and covers the amplituhedron is called a tiling. When the amplituhedron is a convex n-gon, which is a very known case, tilings are just triangulation of n-gons. So it's an open problem to finding and classifying all tiles and tilings when m is greater than 2. And in general, tiles and tilings have very beautiful combinatorics. I could give entire talks on this that are related to tropical geometry, something called the magic number. But also, crucially, it has relations to cluster algebras. Okay, that's the last background material. We already heard something about cluster algebra, so I won't be too detailed. But feel free to ask me later if you want. So cluster algebras are a class of commutative rings with remarkable combinatorial structure. And they have a distinguished generators called cluster variables that are grouped into overlapping sets of same size called cluster. And there are relations among them that are encoded by mutations and quivers that are more combinatorial, introduced by Foming and Zewicki in the 2000s. So in practice, you start with an initial cluster, so a set of cluster variables, and you obtain all the other clusters by some mutations. So for example, if you start with a cluster bold x, and you want to mutate the cluster variable little x, by doing this, you obtain a new cluster where you remove the old cluster variable and you add the new one, x prime. And x and x prime are related by a relation of this type, where m1 and m2 are monomials in the cluster variables of the old cluster. So, and in general, we can also keep some variables, cluster variable frozen, means that we never mutate them. So there are cluster algebras with frozen variables. And the last thing we need is that a collection of cluster variables is said to be compatible if they can be found in a common cluster. Okay. And a very important result by Scott is that the Grassmannian itself has a cluster structure. So in particular, the coordinate ring of the Grassmannian is a cluster algebra. We will denote as A, GR, M, N. And in particular, in the case when m equals 2, this is a very simple combinatorics, and it's perfectly understood in terms of triangulations and arcs of n-gons. But in general, for m greater than 2, the cluster structure is quite complicated. And as you expect, when m equals 4 is the one that actually is related to scattering amplitudes in physics. So it's very worth exploring and understanding it. In general, it has an infinite number of clusters, cluster variables. Cluster variables are polynomial of Plucker coordinates that can have arbitrary degree. And in general, there is not an easy combinatorial rule to understand when two cluster variables are compatible. So when they belong to a common cluster. Okay, next step, I would like to mention how these topics, positive Grassmannian, amplitude-hedron, and cluster algebras, are related to scattering amplitudes. So we move back to amplitudes in planar n equals 4 superior Mills. And we know that they admit an integral representations in terms of an integrand that is a rational functions of external kinematics and loop momentum. And we already seen also in this conference that the residues of the integrand on the 4L dimensional variety where a maximal set of internal propagators goes on shell, also said maximal cut, is called the leading singularity. So leading singularities are very important to understand the singularity structure of scattering amplitudes. And in particular, can be expressed as sum of building blocks called Yangian invariants, Yi. And in particular, the key connection with the positive Grassmannian is that each Yangian invariant corresponds to a certain 4K dimensional cell S sub Gi in the positive Grassmannian that is labeled by a certain Plebit graph Gi. So this comes from all this series of works. And in particular, if you really want to compute the Yangian invariant, you can extract it by something called the canonical form of the image of the positroid cells in the amplitude-hedron, which is also important. But in general, we also want to mention that when the Z tilde map, the amplitude-hedron map, is injective on the tile, is injective on the positroid cell, we say that the Plebit graph is intersection number 1, and also basically the image on the amplitude-hedron is a tile of the image of the positroid cell is a tile of the amplitude-hedron. In this case, the Yangian invariant associated to this positroid cell is a rational function of external momentum, and the poles of this rational function are facets of our tile. Whereas when the map, the amplitude-hedron map, is d to 1, where d is greater than 1, then we have the case of intersection number d. And in this case, the Yangian invariant associated to the positroid cells is the sum of d functions that have algebraic singularities, also called the non-rational Yangian invariants. I also put a caveat here is that when you talk about intersection number, we're actually looking at the amplitude map as the rational map on the complex Grassmannian, but this is more maybe for experts. Okay, so back to the amplitudes. The amplitudes can be expressed as the tree-level amplitude can be expressed in terms of these Yangian invariants as a certain collections of rational Yangian invariants in particular, certain collections of Yangian invariants, whereas the loop-level amplitudes can be expressed as a combination of multiple polylogarithms with some Yangian invariants as coefficients. And as we've heard many times, these can be the singularity structure of the multi-polylogarithms can be encoded in the symbol letters. So AI1 up to AI2L are called the letters. And in this structure, in this scenario, the direct connection with cluster algebra can be phrased by summarizing the following cluster conjectures. The first one was that all the rational letters appearing here in the amplitudes are actually cluster variables of the Grassmannian 4, n. Whenever they are rational, adjacent pairs in these words are compatible cluster variables for the Grassmannian 4, n. And finally, the connection of poles of a rational Yangian invariant that you can find here, for example, are compatible cluster variables for GR4, n. So there is a lot of cluster structure that relates the singularity of Yangian invariants, the letters that are appearing in the amplitude. So this was part of this work here. Also, an observation is that until now, every known algebraic letter that has been found is also actually a singularity of some non-rational Yangian invariant. So the Yangian invariants themselves are encoding a lot of information about it. Okay, so there is a star. Of course, we know that multiple polylogarithms are not enough, so we have to go beyond them. But I think it's still like an open question to understand how the cluster structure interplays with elliptic multiple polylogarithms or lambda leading singularities and Calabi-Yau's integrals over Calabi-Yau manifold. So this is, I'll leave it for future work. Okay, going back to tree-level amplitude, I mentioned that the tree-level amplitude can be written as a sum of certain collections of rational Yangian invariants. So the Brito-Cacciazzo, Feng-Witt, and BCFW recursions tells us exactly how to find these collections. In particular, they found the recursions that express three-level amplitudes in n equals 4 superior mills as a sum of certain Yangian invariants. And these sums, I call them BCFW expressions to be short. And each Yangian invariant that appears in these BCFW expressions corresponds to a certain positoroid cell by what I mentioned before, that these are called BCFW cells. So in our previous work, we proved one of the major conjecture that was in the original paper of the amplituhedron, which is if we have a collection of Yangian invariants in a BCFW expressions, and these are the corresponding positoroid cells, then if we consider the collection of their images in the amplituhedron, then this gives a tiling of the amplituhedron. And in particular, different ways of performing BCFW recursions gives different tilings of the amplituhedron. Other words, like different BCFW expressions corresponds to different tilings of the amplituhedron. So as I mentioned, this was one of the major conjecture introduced in the original paper for the amplituhedron and gives a geometric meaning to the BCFW recursions entry-level amplitudes in n equals 4 superior mills. In the special case of a single standard BCFW tiling, it was proved a few years before by a subset of our collaborators. Okay, I'm telling you this to connect further the amplitudes to the amplituhedron, but mostly I want to mention that the key ingredients of our proof were actually being able to express images of BCFW cells using cluster algebras. So the key point was trying to figure out how to describe these images of BCFW cells in the amplituhedron. Okay, so here I want to be kind of schematic, but BCFW cells can be obtained recursively. So if you have two BCFW cells and with the Plebit graph GL and G right, you just have to stick a Plebit graph here and Plebit graph here inside this Plebit graph, and then you will obtain a Plebit graph of the new BCFW cell. So it's a kind of recursion. And here the purple one is also a core because we use it to generate these kind of recursions. Also, I want to mention, for who is familiar with BCFW recursion, this is a formulation in momentum twistor space, but it's not relevant for what I'm saying. It's just that in momentum space or spinatoricity, the Plebit graph will look like different. So what we showed in our previous work is that if SG is a BCFW cell, then its image is a tile for the amplituhedron. But importantly, we showed that each BCFW tile, so this image of the BCFW cell in the amplituhedron, is the region in the Grassmannian where a collection of compatible cluster variables that we denote as X sub G for the Grassmannian four-domain have a definite sign. So there is for each BCFW cell, there is a collection of compatible cluster variables that describes its image in the amplituhedron. And I just want to mention as a corollary, this also proves that the poles of Yangian invariants in any BCFW expressions are compatible cluster variables. That was one part of the conjectures from early on. But my main point is I wanted to understand how can we generate compatible cluster variables. So for each BCFW cell, we want to have a collection of compatible cluster variables. How can we build these collections of compatible cluster variables? So in order for that, there is the idea of cluster maps that I want to summarize in this way, that a map from two cluster algebras, A prime and A, is called a cluster map if psi maps any compatible cluster variables of A prime into a collection of compatible cluster variables of A. So here there are two non-trivial things. First, each cluster variable goes into the cluster variable, but also the compatibility information of which cluster variable is together in a cluster is preserved with this map. This is true up to some Laurent monomials in the frozen variables. So cluster algebras can be defined up to frozens, and there is always going to be some frozen variables that can be factored out from this map. This basically summarizes informally the framework of cluster quasimomorphism by Fraser in 2015. And indeed, that's how we proved our description of BCFW cells in the amplituhedron. We show basically that the collection of compatible cluster variables that we need for the BCFW tile is the image of a cluster map of the collection that we need for the smaller BCFW tiles. So if you have a collection XGL here and XG right here of compatible cluster variables, then there is a cluster map that maps it into our collection of cluster variables for the bigger cell. So basically, this guarantees that by induction that if these two are compatible cluster variables, this is also a set of compatible cluster variables. However, I mean, we still have a mystery of like, how do we find cluster maps? Like, it would be nice to have this type of maps, also because most of the statements in physics, in the amplitudes, are about compatibility of cluster variables. So it's nice to have a map that maps compatible cluster variable into compatible cluster variables. And also, lots of the Yangian invariants themselves are often built recursively. And so having a map that kind of reflects this kind of recurrence is very useful. So let's have a closer look at the BCFW promotion case. So we start from the Pebby graph that generated BCFW cell, and look at the core, what we call the core. And we also made it bipartite, adding some extra black vertices. What we want to do is for each black vertex, we want to add a vector in C4. And we call them Z if they are outside, and we call them V if they are inside, internal in the graph. What we want to do then is impose, for each white vertex, we want to impose a linear relations between the vertices, the vectors that are touching the white vertex. For example, for each white vertex, I want to impose a linear relation between V1, ZA, and ZB, so that impose that V1 is in the span of ZA and ZB, and so on. So for each white vertex, we have a linear relations or kind of collinearity condition. Then finally, using these relations, I want to solve each internal vector in terms of the outside vectors, ZA, ZB, ZC, ZD, and Zn in this case. For example, we can show that V1 can be chosen to be this linear combination of ZA and ZB that can be interpreted as living at the intersection of the two planes spanned by ZA, ZB, and the three planes spanned by CD, and so on. So V2 can be found in a similar way. So in this case, I can find a unique solution up to the scaling of the vectors of this problem of solving each VI in terms of the external ones. And then I want to use this to define a map. So I put some blobs on the left and on the right, and I define maps on the left Grassmannian and map on the right Grassmannian by basically substituting the column vector in the Grassmannian here with the vector that I found at this corresponding vertex. And similarly here, I read the columns in this Grassmannian, and I substitute them to the vectors that I have attached to the boundary vertex. So N goes to something proportional to V1, D goes to something proportional to V2, and so on. So, and this is how we define the map. And here I use this symbol because it's up to a scaling. We can rescale, everything is defined up to rescaling, so we have to choose a specific scaling, but conceptually, this is what's happening at each side. So this is the same map. I just wanted to report it. And what happens now is that if we take, for example, a Plucker coordinates in the left Grassmannian, and we apply this map, the Plucker coordinates, for example, I, J, and L, and B, what happens is that if we look at the formula, we have to insert the vector B in a combination of vector V, B, and VA. And this gives a quadratic in the numerator and the semi-denominator. And we recognize that the quadratic in the numerator, this is a certain notation that we use, it's actually quadratic cluster variables for the Grassmannian 4, n. And this is not a coincidence, because we show exactly in the paper that this map that we define is a cluster map. So it maps cluster variables, like the Plucker coordinates, into cluster variables, like this one, up to some frozen. So we can always factor out, we have to consider some factors that we have to drop. And there is going to be a cluster variable left. So this is an example of how we generated the cluster map for the case of the BCFW. But we thought about how do we generalize this? And I'm going to use the same example in the graph, but the description is going to be more general. So if we start with a Plebig graph that has intersection number 1, and we make it bipartite by adding some black vertices, then we do the same thing as before. We add for each black vertex a vector in C4, and I call them Z for the external and V for the internal. And then for each white vertex, I impose a linear relation. And then I solve all the internals in terms of the externals. And we also show that because we chose C core to be intersection number 1, basically this has a unique solution. So having this problem a unique solution is equivalent to having intersection number 1 there. And afterwards, what do? Is we place disks, one disk for each of a face of our playback graph. In this case, we place one disk here, but I could place it also in other places. And each disk I consider the vertices on the disk, and I connect each vertex of the disk to a vertex on the core. So a vertex here is connecting to here, a vertex here is connecting to there, and so on, in a way that is planar, so I don't cross all the edges. Okay, and once I do this, I use this to define a map from the cluster algebra of the product of all Grassmannians in the disks, on the input disks, to the cluster algebra of the whole Grassmannian for comma n. And the map is very simple. For every Grassmannian GR for NL, on a disk, I substitute a column vector to the vector that I find connected to it. So in this case, it's going to be VBU. And as usual, I have some freedom of rescaling. So there might be that you have to tune in some global scaling, but that's basically it. We call this data of a core with a collection of disks that are connected to the core, a playback tangle, inspired by the planar tangles in the work on planar algebra by Jones. Okay. So the proposal is that we want to use these promotion maps defined by playback tangles as cluster maps on the Grassmannian. In particular, this tells that intersection number 1 playback graphs that corresponds to rational Youngian invariants or amplitude tiles are a way to generate maps on the Grassmannian, cluster maps on the Grassmannian. Okay, I have a few minutes left. I wanted to mention that this is very quick. I want to mention in general, there is no known combinatorial classifications of all intersection number 1 cells. There is an algorithm to compute it, but it's not. There is no nice combinatorial criterion. What we did is we classified all the trees that are intersection number 1 that we call ampli trees. And for example, the BCFW one was just the simplest one, but for higher K, there are others. For example, there is something called the Spurian or the chain tree. And for each of this, we can generate cluster maps. So we've showed that for all the things here, these generate cluster maps in the Grassmannian. So there is an entire zoo of possibilities for which the BCFW was just the first one. And this generates many, many possible maps in the Grassmannian. I just wanted to mention in the last few minutes that then we talked about how to generate maps starting from intersection 1 playback graphs. But what about when we go beyond intersection number 1? So if you have, so here I consider the example of the 4-mass box. 4-mass box is basically the playback graph associated to the leading singularity that you obtain from the cut, the box coefficient, the 4-mass box coefficient in n equals 4 superior Mills. And the playback graph is the one in purple. And it's known that if you try to find these vector configurations, you will find 2 solutions that satisfies all the conditions I told you before. So that ends for it's like plus or minus. But the other feature is that you cannot write these internal vectors as function of the external vectors in a rational way. You have to introduce some algebraic functions. And indeed, the internal vector x can be written in terms of the external, for example, z7 and z8 here, by a coefficient alpha that has a square root inside. And this square root is exactly the square roots that appear as an algebraic letter in the symbol. I mean, it applies as a Landau singularity, and it's important for the algebraic letter. And here I rewrote this in terms of ABC, that each is a cluster variables in the Grassmannian, and these are 2 sums of cluster variables. I think the formula in the literature is slightly different, but they're, of course, the same expression. Just here, I wanted to highlight the structure in terms of cluster variables. So what do we have here now? That now the map is taking the vectors, for example, 7 in this little Grassmannian, and it's mapping it to x. It's taking the vector 2 and it's mapping it to v1. But then these vectors are algebraic functions, so we cannot get cluster variables out of it, right? So if we, for example, apply this map to the Plücker coordinates 1, 2, 7i, we get this, which is a sum of 2 Plücker coordinates with this alpha plus or minus that is very nasty square root. So this is an algebraic function. So we cannot claim anything about mapping cluster variables into cluster variables, but we can claim something else. We can claim that even if psi, of course, is mapping something to algebraic, it still preserves positivity. Yeah, I'm almost done. So, sorry. Yes. And the psi plus or minus preserve positivity of cluster variables. So if you consider psi of x is a positive function, a positive Grassmannian. And this is very non-trivial because this is positive, and alpha is negative. So in particular, the algebraic singularities of Yangian invariants where n is greater than 9 and k equals 3 are actually obtained using this map. And this shows that they are positive on the positive Grassmannian. If you give me 1 second, I will finish with a positive outlook, which is the whole direction is trying to understand the singularities of n equals 4 to Mills. And there is this positivity phenomenon for which it's conjectured that actually amplitudes are regular on the positive Grassmannian. In other words, all the singularities are expressed as a vanishing of a function that is positive on the positive Grassmannian. And so when this function is rational, it is conjectured that it's a cluster variable from the positive Grassmannian. And so we know the cluster variables are positive on the positive Grassmannian. And in particular, we also suspect and conjecture that all the singularities of rational Yangian invariants are images of cluster promotion maps. That also implies that they are cluster variables. But whenever f is algebraic, what happens is that there is not a general mechanism to explain why they should be positive. So there are some works relating to limiting rays and cluster algebraic functions that try to explain. But in general, there is no mechanism to prove that in general they're positive. And what we show is that the singularities of non-rational Yangian invariants are actually images of some promotion maps. And at least for the case of the 4-mass box, these promotion maps preserve positivity. So there is a kind of way to think about positivity. Okay, so I'm just going to leave it to say that these cluster promotion maps can, of course, shed light independently on the cluster structure. Even if you don't care about scattering amplitudes, you want to think about cluster algebras itself. Or if you care about scattering amplitudes, that's why we are here. You want to understand how are these relevant for studying symbol letters. For example, are symbol letters images of promotion maps? Okay, thank you so much.